So here we have a circuit, a problem that I have not taken from an exam but from an assignment. So it's a bit larger, especially when the value of R is not given and it has three different possible values given, and we need to solve the circuit or find the response for each case. So basically I am going to solve one of these, and you are going to solve for the other two cases. And the methodology is same, except the form of the response, the expression for overdamped, underdamped, critically damped are different. So here we need to find this voltage V should be small voltage. This Vt is to be found, and once this switch closes at t is equal to 0, now we get this circuit separated from this circuit, because this inductor shares this path. This is a short. Why would the current go here, the difficult path, and not flow from the short? So basically this wire is going to be shared by this circuit and this circuit. So basically the current in this wire would be because of this as well as this. However, we are not interested in finding the current through the switch. We are only interested in finding the expression for this Vt. So for different values of R. So suppose we begin with taking the value of R to be 2 ohms, the first case. The alpha, this is a parallel RLC circuit, is 1 over 2 RC, is going to be 1 over 2 into 2 into C, which is 0.01 millifarad, 10 millifarad. So basically what do we get here is 1 by 4, which is 0.25. 0.25 divided by 0.01 is 25 Nepers per second. And omega naught, omega 0 would be 1 over under root square root of LC in the denominator. 1 over 1 Henry, and C is 0.01. 0.01 has a square root of 0.1, and 1 over 0.1 is 10. So with 10 radian per second, we have alpha greater than omega 0, which implies a response that is overdamped. So I believe for the case of 5 ohm it would be critically damped, and for 6 ohm it may be underdamped, but you have to solve it for yourself. So let's try it. By the way, for 5 it will be 2 into 5, which will be 10, 1 over 0.1, which is 10. So you see, for 5 it is critically damped. Alpha would be 10 because omega 0 is not going to change. So alpha is equal to omega 0, which implies that this is a critically damped circuit. And for the case of R to be 6 ohms, it is going to be 12. It's going to be something that obviously is going to be smaller than, what would that be? 6, 12, 1 over 12, 1 over 0.12. I hope it would be something like, you have to solve it, but 8 Nepers per second, and so alpha is less than omega naught, which is the case of underdamped. But do solve it, please. Do not rely on my quickly guessed value. So let me take this and solve for a critically damped, because in the previous two problems I have solved for overdamped and underdamped. Let us solve for critically damped here. So here, when the circuit is critically damped for R is equal to 5 ohm in a parallel RLC circuit, the expression for Vt, the voltage across each component, is the same. So V at infinity plus, which in the case of natural response circuit we know is 0, plus A1 T e raised power st. This value of s is going to be the same because both roots are going to be same and real. A2 e raised power, one term will have t, the other term will not have t in it. So, and this s would be equal to minus alpha because the other term will be 0 because alpha is equal to omega 0. So we are going to get this equal to minus 10. So basically Vt, because V at infinity is 0, Vt would be equal to A1 T e raised power minus 10t plus A2 e raised power minus 10t. It make absolutely no difference whether you put t in here or here, but one of the term is going to get a t, the other term does not have the t. So which of the constants is called a1 and which one of the constants is called a2, it does not matter. Once you declare the term with the t to be a1, however, then stick to your assumption throughout the question. If in the next question you take this to be without t and you call this a1 and put t here, for that question conform or stick to that notation. Be consistent in one problem. So what do we get here? We need to find the value for a1 and a2, and exactly the same method is to be followed for t is equal to 0. We have v at 0 plus equal to a1. So now putting 0 makes this whole term 0. So we get e raised power 0 is 1, a2 equal to this thing. So what is this voltage at t is equal to 0 minus before switching, because before switching because of this circuit. So let us find that. This V is exactly the same V that is across the capacitor. So how would the capacitor be behaving in a circuit with a voltage source and this switch was open, so it's not there? A short circuit, inductor have become short, resistance remain there, and the capacitor has become open, and we want to find this voltage, which obviously is the voltage across this resistor, and this is 5 and this is the case of 5. So both resistances are of equal value, so this voltage is going to be divided between these two resistors, so we get 2.5 volt as the initial voltage. This voltage is going to be unchanged because of the action of the capacitor. It's going to resist the sudden change in voltage. So this is one equation. A2 is equal to, so let us ignore this V here because these are treated as constants, although they are not dimensionless constants but carry the same dimension as that of the voltage, because in fact this A1 does not have the dimension of voltage but voltage over time, voltage V over S, because this has dimension of S, SS going to cancel out. However, A2, the dimension of A2 is V. But for maths, let us put we are more interested in the value 2.5. Anyway, let us take the dimension along as well because we need to be technically correct. So let us now take the derivative dv and put t is equal to 0 in it. In the derivative here, what we are going to use the uv formula. So a1 derivative of t, which is 1, and then putting t is equal to 0 is making this 1, so we get a1 here, plus when we take the derivative of this thing and not of t, then putting t equal to 0 will make this term 0. So the other term will become 0, and now taking the derivative here, we are going to get minus 10 a2. See, this will become 1. And what is this thing? dV by dt for the case of a capacitor, this is equal to the capacitor current at 0 plus divided by the capacitance. And what is this thing? For this circuit, for the capacitor, the resistor and the inductor to be in parallel with this V and this IC, this current is V over R, this current is V over R, and this current is IL. We need to find the value of this current in this case at t is equal to 0 plus. This value of this current would be 5 divided by 10 or 0.5 ampere. Now looking at this direction of IL and this direction, we know that IL at 0 minus would be minus 0.5 ampere and IL 0 plus would be minus 0.5 ampere as well. So we know we have a current upward going in here of 0.5 ampere. This current downward is Vt at 0 plus, V0 plus by R, and V0 plus is 2.5 and IC. So basically we can, using the node voltage method here or KVL at this node, we can write IL plus IR plus IC equal to 0, and for a particular time IL at 0 plus IR at 0 plus IC at 0 plus is also equal to 0, and IL at 0 plus is minus 0.5, and this is V 0 plus over R plus IC at 0 plus equal to 0. So what is IC at 0 plus equal to? All these things go over there. 0.5 plus what is this voltage is 2.5. What is this R is 5 is 0.5. 0.5 plus 0.5 is 1. So IC at 0 plus is 1. So this is 1 and C is 0.01, which means this is 100. So the equation with A2 given, A2 found, A1 minus 10 into 2.5 is equal to 100. So A1 is equal to 100 plus 25, which is 125. The dimension for A1 was volt over second. So both of the constants are known. So therefore Vt would be equal to A1, which is 125 t e raised to power minus 10 t plus 2.5 e raised to power minus 10 t volts, or can be written as there are several ways of writing it, but let us just take this term constant, or 2.5 along with as well. We can write this as 125 over 2.5, solve it, t plus 1. So this is the expression for voltage for the case, for the B part, for the case where R was equal to 5 ohm and the circuit critically damped. So you can solve for the other cases and it's not going to be a difficult problem.